So I'm away from class today, but hopefully we'll be able to keep moving through some material. So watch this video and follow along on the worksheet provided. So we're talking about covalent compounds today. So they're also known as molecular compounds. So you'll hear them interchangeably throughout the discussion of these in the course. And so these are really molecules that are made up only of covalent bonds. And really what a covalent bond is, it's just sharing electron. So instead of before where we were thinking of something like sodium and how it would give away that electron to become a positive charge, really now we're going to have, let's say we'll have chemical X and Y, and it has something here and here, and these things will be sharing each other so that way they create a bond that's closer. There's no donation, there's just filling up space with these electrons, and more on theory about this to come later on, especially when you get into chemistry in grade 10 and grade 11. So right now we're talking about these, and these are really the opposite of ionic compounds. So like I said before, electrons are donated. And for the most part, these things experience strong intramolecular forces. And just as a side note here, intra in science means within something, and inter means outside, so in a relationship to something away from itself. So here they have strong intramolecular forces. And these hold the compounds together. So you look at water, it's really holding itself together. But and these things also have weak intermolecular forces, meaning that the molecules aren't really attracting towards one another, but the strength within the molecule is very strong. So here, if you look at this, this is an example of sodium chloride. Sodium's in pink, and chloride atoms or ions is in green. And these things are really easy to break apart from one another, but their total structure is very strong. So it's really strong intermolecular, but it's weak intramolecular, and that's characteristic of ionic compounds. But here in water, which is a covalent compound, we have really strong intramolecular forces where this oxygen, the red oxygen, is attracted to the hydrogens, but these water molecules could really care less about each other. They're just kind of floating around in space, and they're not too worried about stuff. So dealing with the properties of covalent compounds, for the most part you can think of these as opposite of ionic compounds. So ionic compounds had high melting and boiling points. Well, these things have low melting and boiling points. Ionic compounds were hard and they were easy to break, and these things are soft, right? And they're kind of brittle. They're softer to deal with. And of course, these things are poor electrical conductors. So if you remember from your lab on Tuesday, if you dealt with the vegetable oil, there really wasn't much conductivity going on in comparison to, let's say, table salt. An interesting note here is that these molecules will maintain a distinct shape when going through phase changes. So a water molecule like this will look the same no matter what phase it's in. So this water molecule will just be closer together in ice, really far apart in gas, and it'll be somewhere in between when it's liquid water state. So the only thing that really changes is their orientation to other molecules of the same kind. So in ice they're really close, in gas they're really far, and then liquid in the middle. Well, what are these things made of, right? So before an ionic compound were a metal and a non-metal. Well, now we're dealing just with metals here. Or sorry, non-metals. So these are non-metals only, and we're dealing with hydrogen, which is surprisingly a non-metal. More on that to come. And then we're dealing with our group elements over on the right-hand side. So our halogens and our non-metals and the metalloids, actually. So scientists have been debating over this for quite some time, but for our intents and purposes, we're going to use the green bits here, the metalloids, as non-metals when bonding in a covalent fashion. So before we move any further, I'd like for you to take a couple minutes and think of some examples of covalent compounds. You can research them, you can write them down on your sheet, and you can talk in partners or pairs, and just pause the video and take a look at that before you move on. Well, how do these things really work? How do they actually bond? So before we had ionic bonding diagrams, and now we're going to have covalent bonding diagrams. So as we've seen them before, atoms really love to be stable. And before that was from donating and accepting electrons, but now they're from sharing. And in covalent bonds, this stability comes from a special rule called the octet rule, which means that there has to be 8 valence electrons around the elements of carbon, nitrogen, oxygen, and all of the halogens. And it doesn't have to own 8 of its own, it has to be shared with it. All right? So this is where it's a little bit different than ionic. One thing to know is that each bond requires 2 electrons to form, and we really have to think about valence electrons when we're looking at these. So the rules that are on your worksheet, you can follow along as we go through this example for water, and I'll also do one for ammonia, so NH3 down there. So for water, we first have to do some valence electron bookkeeping, so we have to figure it all out. So for hydrogen, I know that I'm going to have 2 hydrogens because it's H2, and I'm going to have 1 valence electron per hydrogen because it's the first thing on the left-hand side of the table, giving me a total of 2 electrons. For oxygen, I know that I'm going to have 6 valence electrons. I'm going to have 1 oxygen. Might as well keep it in the same way for each time. So we're going to have the number of atoms first. So I'm going to have oxygen, I have 1 of them, and I'm going to have 6 valence electrons. And oxygen, just remember looking at your periodic table, it's the 6 positions over to the right, and that's going to give me 6 here. So I'll have a total of 8 electrons altogether. So we have to decide on a central atom, and for here, usually it's the one that's the least abundant, and we'll never ever see hydrogen as the central atom. So that's one hint for us. So I'm going to have oxygen here, I'm going to have hydrogen off to the side, and hydrogen off to the side. Now I know that I'm supposed to fill in the bonds, so I know that bonds are worth 2 electrons apiece. So I have 1, 2, 3, 4. So I'm going to take 4 away from this, and I know that my total all now is going to be 4 electrons. If I have some remainders, I'm going to satisfy the outside electrons, and I know that hydrogen really can only take 1 electron. So I'm not really going to put any extra here because then that would be too many, and that would make hydrogen negative, and that's not the case. So really I'll put my remainder electrons on this oxygen. So I'll put 1, 2, 3, 4, all leftovers go onto the central atom, and this right here is totally done. And the way we know it's done is because oxygen does have an octet. It has 1, 2, 3, 4 electrons attached to it in forms of bonds, and it has 5, 6, 7, 8. So it has 8 electrons around it altogether. Moving on to the next example, let's do this one for NH3, so a form of ammonia. So I'll know that N is equal to, I have 1 atom, I have 5 electrons per atom, which will give me 5 electrons total. And I know that I have hydrogen, which I have 3 of, and I know I'm going to multiply that by 1 electron per, which is going to give me 3 electrons. And I'll have 8 electrons altogether for this beast. And because of our rule from before, I know that nitrogen is going to be the central atom because I can't have hydrogen as a central atom, and usually it's the one that's the least abundant that goes in the middle, and I'll have my hydrogen surrounding it. And I remember that I have 2 electrons per bond, so I have 1, 2, 3, 4, 5, 6. So I'm going to take away 6 electrons here, and I'm left with 2 left over. Now I'm going to place these leftover 2 electrons right on the central atom because hydrogen's already happy, it already has all the electrons it needs. So we have 1, 2 in this bond, 3, 4, 5, 6, and then 7 and 8 in this lone pair here. When we're writing these, try to keep the lone pairs, they're called, so bits of 2 electrons, grouped together when you're putting them on the central atom. Ask questions about that if you don't really quite understand. So here, nitrogen does have an octet, and it's very happy. I'm going to leave these ones for you to do. They're on the worksheet on yourself, or on the worksheet itself, and you can take a look at them. And on Monday of next week, when I get back to class, we will go over these together and we'll make sure that everybody's on the same page. Now, sometimes you'll run across examples where we don't have we have unmatched electrons, where maybe we don't have an octet that's necessary. So this is a little bit of a different concept. So I'll show you the way that we do this with carbon dioxide. So carbon, I know, is going to have I have one atom of it, and I'm going to multiply this by, I have 4 electrons in its valence shell for a total of 4 electrons. And I'll have oxygen, I'll have 2 of them, and I'm going to have 6 electrons per oxygen, meaning I'll hang up 12 electrons altogether, and I'll have 16 electrons for this molecule of carbon dioxide, right? So I have 16 valence electrons. Now, carbon's going to be our central atom, and it usually is in these types of examples. Carbon will most likely be your central atom if you see it, if it exists. And I'll put my oxygens off to the sides here, away from it. Now, I know that my first inclination here is to create a bond by drawing a line in between the carbon and oxygen, so I just used how many electrons in this? And if you guessed 4, that's correct. So we're going to go and we're going to take away 4 electrons because there's 2 electrons per bond, giving me 12 electrons total left over. So here I'm going to satisfy the octets necessary on the outside the outside oxygen. So I'll put 1, 2, 3, 4, 5, 6. And remember, one of the rules is to spread all of these electrons out evenly across the outside atoms. So 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11, 12. As of right now, I've used all 12 electrons, so I have 0 left. And I'm pretty satisfied with this because oxygen has an octet on both sides. But you might be asking, well, hey, carbon doesn't have an octet yet. So it only has 1, 2 electrons in here, 3, 4 electrons in here, and it needs 8 for it to be happy. So this is where this idea of a double bond comes up. And yes, if you're thinking, if I have double bonds, can I have triple bonds? And yeah, you might run into an example of that really soon. So here, what actually happens in order for everything and everybody to be happy in this situation, I'll do this in a different color, is that these electrons from oxygen will come down and it'll create a secondary bond between oxygen and carbon. Same with a couple of these things over here. Now notice it doesn't really matter where you grab these from. These are just in 2-dimensional planes. In reality, it's really complex where these electrons go, but you can pick any ones you'd like. So these electrons will also come in and they'll make this newfound bond. So if I'm going to redraw this, which usually we do after we create this type of diagram, we're going to have carbon, oxygen, oxygen. We had our original bonds. We have our original electrons that still exist on the outsides of oxygen. But now we have these new bonds that are created between carbon and oxygen. So if I'd like to go and check these things, I want to see if carbon has an octet now, and it certainly does. So 1, 2 in this new bond, 3, 4 in the old bond, 5, 6 in another old bond, and 7, 8 electrons are surrounding this carbon. 1, 2, 3, 4, 5, 6, 7, 8 around oxygen, and the same on the other side. So we know that this is a good diagram. Everything's happy. We have double bonds in this. So whenever you have something in the middle that doesn't have its octet quite yet, you must think about double bonds or maybe even triple bonds. I'm going to leave you with these to do over the next little bit of your time. Ask questions, work in groups, think about it, and there's tons of videos and tons of stuff out there. I made this to match up with the worksheet that we had. However, if you were to go and just Google covalent bonding examples or covalent bonding Lewis diagrams, I'm sure you're going to find lots of resources. I'm also available to answer questions at any point through email, so just send me a quick email and hopefully I'll get back to you as soon as possible. Have fun and good luck.